Okay, so you're going to program up your first program. And to do so, you are going to derive a program for evaluating a polynomial. And you're going to derive its proof of correctness hand in hand with the code itself. Now, what do we have here? Well, you've opened up the file that we pointed you to. The first thing I want you to do is to save a copy of this so that you can always go back to the original if something goes wrong. And what do we have here? Well, we have a description of what it is that we want you to do. We want you to compute a function that evaluates a polynomial. The coefficients are stored in array P. The point where you want to evaluate is stored in X. And the exercise itself is described in a live script. And that's nice because it allows the description to be interleaved with executable boxes that have the actual code in it. And what we've done here is we've introduced some executable boxes that actually test the program that you are going to create. So here we set n to be 4, so we'll have 4 coefficients. Those are randomly generated integers between -1 and 2, and we're going to set that up as an n by 1 array. And then x is the point where you evaluate it, and we take everything to be an integer so that when we compare against the native routine that's part of MATLAB, we don't have to worry about round-off error, making the result not exactly the same. And then here we just call the routine that you are going to implement. We're going to take the loop invariant that we came up with in the video, which I'm going to call loop invariant 5, and from that you are going to derive algorithmic variant 5 for this operation. Now the native routine that evaluates a polynomial orders the coefficients in the opposite direction. Oops, here I need to fix this. And that's actually what the native routine does. And therefore we need to reorder the coefficients in order to be able to compare. That comparison is done right here, but notice you are going to derive the program to be correct, so it should never tell you that something is wrong. The only thing that you should expect to come out is that the answer is consistent with what the native routine from MATLAB itself computes. And then down here I've already created part of the function for you. This is the function. I here check whether this indeed is a column vector that's being passed in for P, and then I check that the X is actually a scalar, and then here I've already gone ahead and extracted n, which is the size of the array, so that you're ready to derive the algorithm. And here there are some executable boxes that you're going to have to modify, interleaved with some text boxes in which I've created the specification for the program segment with a precondition up here and a postcondition down here. So I'm going to go ahead and annotate this code segment with the loop invariant. You don't need to do this, but if you want, you can. What you are going to do is to then actually derive the different pieces of the program to be correct. So how do we annotate this with the loop invariant? Well, we take this and we copy it over and we put it up here. And we do p underscore inv to fill that in. And then the loop invariant was chosen to look like this, where the 1 is replaced by a k here and by a k here. Okay, so we have this, and then what we also need to do is say and 1 is less than or equal to k is less than or equal to n plus 1, and then everything works out. Okay, and then we want to go and indicate everywhere where this loop invariant must be true. And it has to be true there and there. And I like to indent things, so I'm going to put, and the only way I know how to indent is to put some dots there. And then I want to copy this over down here so that the indentation is the same. And then up here it has to be the case that G is also true. And down here it has to be the case that G is not true. Okay, so what I want you to do is I want you to go and look at what's here after the loop, and systematically derive the loop guard G, and I'll see you in the next video.